Assalamualaikum semua. Okay, we are from group 3. We are going to present about experiment 2, single stage compressor. Group 3 consists of Muhammad Al-Hafiz, Muhammad Afan, Muhammad Daniel Aikal, and myself, Muhammad RC. Okay, next. Okay, for the abstract. Compressor are the chemical device that employ internal energy to raise the pressure of compressible fluid or gases from low to high pressure. In addition, a compressor is a system that functions in a constant rate. An open process system is defined as mass breaching its boundary as the process takes place. By delivering work from an external source through a rotation shaft, a compressor raises the pressure of a liquid. This is an introduction to a one-stage compressor experiment involving energy balance. The objective of this experiment is to see how it is transformed into work. When the power and motor are turned on, the temperature of output A is measured every minute until two consecutive readings are identical. Specific value of 134 degrees Celsius were taken at 31, 32, and 33 minutes. To analyze the heating curve and behavior of the single stage compressor, a graph of outlet temperature T against time is displayed. The outlet temperature of the compressor increased exponentially with time, according to the analysis of data occur and shown the graph. Next one. Okay, for the objective to observe how it transforms to work. Okay, for the introduction, this experiment, the single of piston and pressure sensitive valve are used. Single stage air compressor is made to power a single cylinder that compresses air with a single piston rotation. The cylinder is attached to a force supply that provides the necessary force to compress the air. Piston compressors are another name for single stage compressor. The following is the procedure that takes place within a single stage compressor. First, air is sucked into the cylinder. Second, trapped air compressed during a single stroke with 120 psi piston. Third, compressed gas moves onward to the tank. The compressed gas in the tank provide energy for the various tools that a single stage compressor is defined to handle.
So, I am Muhammad Al-Hafiz. I'm going to explain about the theory of the experiment. A fixed volume of air is trapped between two sliding vanes driven by an offset rotor in a standard single-stage vane compressor. The volume of air is pressed to the outlet where the area is diminished. Thus, the pressure is higher and it is pressed out of the outlet port. The single-stage air compressor works using the force of a piston and pressure-sensitive valve, which consists of rotary vane type of air compressor coupled to a turn-on mounted electric motor, and it is attached to a spring balance. As you can see in figure 1, this is the schematic of a single-stage compressor.
Hello, my name is Muhammad Afan bin Lubidi. So I will present the apparatus, data and sample calculation of how to get the data. So as we can see, this is the apparatus setup for this experiment, single stage compressor. So in this experiment, we have airflow meter, which the air coming will catch from the atmosphere, and then the air will move through the inlet valve here, and air chamber air chamber we have the compressor, and motor and outlet valve, and lastly is barometric pressure, which we want to uh, read the atmospheric pressure.
For the methodology or the procedure, the first one is the power switch was turned on. The green inlet valve was fully open, which is the turn the valve anti-clockwise to open it. The next step is The initial readings for all parameters given in table 1 were recorded at the beginning of the experiment. A tachometer was used to record the motor speed. N. Next, the motor switch was turned on. 5. The fifth step is by using the red outlet valve, the compressor outlet pressure P2 was set up to 1 bar gauge. To increase the pressure, the valve was turned clockwise. The next step, the spring balance was adjusted to ensure that the indicator on the motor is between the two black lines, prior which is before recording any motor force values. Seventh step is the temperature of the outlet air T2 was recorded at 1 minute intervals by using stopwatch until two consecutive readings are the same. To stop the experiment, the red valve was used to reduce the compressor outlet pressure P2 to 0 bar gauge. The valve was turned anti-clockwise to decrease the pressure. The motor switch was turned off and the power switch was turned off.
So for result and calculation, so this is the data from the experiment. The length first, we should find the length of top, which is equals to 0.2 meter, and the value of compressor sweat volume ataupun or we call it VCOM equals to 276 centimeter cube per revolution, and the specific heat capacity of air CP equal to 105 joule kilogram per Kelvin. Yeah. So the parameter here we have air temperature into the apparatus P naught, we have P1, P2, atmospheric pressure, vacuum into the compressor, air pressure out of compressor, flow V in inch. We have speed, revolution per minute, and motor spring balance in watt and electric power, as we can see in the box on the right hand side. Next, this is the data taken during the experiment. So we should record the temperature for time starting from time equals to first minute up to 33 minutes. So as we can see, when the time is 1, then the temperature is 69 degrees Celsius, and up to 33 minutes 33 minutes. So we get the temperature is 134 if not mistaken. So after that, we should calculate the energy added to air by compressor and or HC and QC, which is energy emitted to the compressor. Next. Alright, this is the sample calculation of how to calculate the QC and HC just now in the table. First, we should calculate the V naught, where the V naught is equals to R T naught over P naught. As we can see, the V naught R is 0.287, and the T naught we should convert to Kelvin. Convert to Kelvin over P naught. So we get the V naught equals to 0.84602 meter cube per kg. And the second method is we should calculate the volumetric flow rate. Volumetric flow rate is V inch equals to 60 times exponent of power of 3. The V inch is 300 per minute, and divide by 60 times of 10 power of 3. So we get the volumetric flow rate is 0.005 meter cube per second. And then we should calculate mass flow rate by using the value of volumetric flow rate and the V naught just in the step 1 and step 2 is now. So we got M of mass flow rate equals to 0.00591 kilogram per second. So from that, we can calculate the HC, or the energy added to air by compressor or by using the formula MC delta T or T1 minus T2. So we got the HC equals to, so as for this HC, we just calculate for temperature equals to 69 minus 28. So we need to repeat the calculation up to temperature for 30, up to temperature for the time equals to 33 minutes. So for this at first minute, we get HC equals to 243.52 watt. And then before we calculate the QC or heat emitted from compressor, we should calculate power of motor using this formula as we can see here. So we get the power of motor equals to 804.35 watt. And then we can move to calculate the QC for the last step, which is using the power of motor minus energy added by air in step 4 and step 5 just now. So we got the QC equals to 560.83. All right, next step. Next slide. Okay. So the question asks for to us to plot the graph of temperature versus time. So as we can see, the graph here, the graph show that temperature is slightly increased against time. Second graph is next slide. Second graph is the graph of energy added to the air versus time. So as we can see, the graph also slightly increased. Energy added is slightly increased with time. The next slide. So this is the third graph. The third graph is the graph of energy admitted from compressor. From compressor versus time. The graph shown is slightly decreased. Yeah, I think that's all for me. I pass to the next presenter. Thank you.
So, my name is Muhammad Daniel Haikal, matric number A19ET0124. So, I'm going to be presenting about the discussion and conclusion parts. So, the first, there are actually three main things that we need to discuss, which is the shape of the graph that was obtained from the results. So, as said from Afan just now, we could there's actually three. So the first graph was actually outlet temp versus time. Second will be the energy added to air by the compressor versus the time, and the last one would be heat emitted by the compressor versus the time. So from the graphs that we that was shown just now, we could see that actually for the first graph it actually increases. Same goes for graph number 2, while number 3 it actually decreases. So in graphs 1 and 2 they were actually experiencing a heating up curve, while graph number 3 was getting a heating down curve. This was actually due to the heat transfer, which is Q. So actually when heat transfers to a system, or we call it heat gain, it will increase the energy of the molecules, including the internal energy of the system. This can also be said for heat transfers from a median, which actually has an opposite effect, or called heat loss, which actually a decrease of energy can be seen due to heat coming from the energy of the molecules in the system. If we can refer back to graph number 2, which we can see it increases from graph of energy added to the air against the time. It happens due to the work that applied into the compressor was given enough pressure and energy for the air to go out of the compressor. So we can actually say that from here that the more the time taken by the compressor, actually the higher the energy added to the air due to the increase of work done by the compressor. Work done will then be changed into energy transfer associated with force acting through a distance. So next slide. So the second part that we need to discuss is actually discuss the energy that is being input to the system when the system heats up. So apparently for a compressor, it actually acts as a supply of energy that actually causes the temperature to actually rise, and eventually it reaches a point that it becomes we can't even see the difference. We can call it constant. That means that it reaches a thermal equilibrium. That also means that energy is being input to the system is being used by the system. Thus, there will be a loss of energy in the form of heat to the surrounding. So the last part would be discussing about the amount of energy loss as heat compared to these two things, which are the work input to the compressor and also the heat added to the air. So the amount of energy loss as heat was actually lower than the work input to the compressor and also the heat added to the air. For this experiment, actually, the heat that was emitting from the compressor, which is Q, was the heat loss, while the energy added to the air by the compressor, which is H, is the useful energy used to compress the air. So the work input that was coming from the compressor was from the power of the motor, which was calculated by Afan just now in results, and it actually stayed constant throughout the experiment. So we know that from the first law of thermodynamics, we know that energy cannot be destroyed or created. So for this experiment, the energy input was changed into heat emitted from the compressor and the energy added to the air. From these results, it shows that the higher the temperature difference, actually, the higher the energy added to the air and the lower the energy loss. This also indirectly means that the compressor actually works better and efficiently at higher temperatures. So next slide. So what can we actually conclude from the experiment? Well, from the experiment, the outlet temperature T2 increases drastically as time increases due to the heating process. And this actually shows that the single stage compressor heats up the air very fast. When T2 actually increases, the energy added to the air by the compressor Hc also increases exponentially, but the heat emitted from the compressor Qc actually decreases drastically. We can see at time equals to 30 minutes, the temperature remains constant at 134 Celsius and does not increase further. This actually means that a steady state has been achieved, and the heat emitted from the compressor at this temperature is the steady state heat loss at a single stage compressor, which is 174.757 watts. The data obtained can be more accurate actually if there were lesser systematic and random errors. However, we can conclude that it does not change the overall shape of the plotted graph, and the experiment is considered a success and achieve the objective of the experiment. So that's all for experiment number 2 from group 3. Thank you.